Thank you for that kind introduction. I'm going to talk about electricity without greenhouse gases and why it's essential to meeting the challenges of climate change. Um, if I can make my slide advance, hang on a minute. Yeah, so it's particularly fitting that I'm speaking to you today from Pittsburgh because Rachel Carson graduated in biology from the Pennsylvania College of Women, which is now Chatham University. It's located just up the street from my Carnegie Mellon office. And as you can see in this screenshot at the bottom, Pittsburgh's region is really proud to count her as one of our own. Today, I'm going to talk about three things. I'll give some basic background on climate science and on the electricity system. Then I'm going to talk about why electric power is critical to climate change first as a leading source of carbon dioxide and other greenhouse gases, and then as the most viable option to replace fossil fuels in many of today's energy system applications. And I'll wrap up with some discussion of the need to expand electric power transmission capacity and some efforts that a number of us are taking to address this problem. Now, to be an informed participant in public discourse about climate change, people basically need to know just three simple facts. Burning coal, oil, and natural gas produces carbon dioxide that enters the atmosphere. Once carbon dioxide gets in the atmosphere, it warms the earth, and that warming changes the climate. And once carbon dioxide gets into the atmosphere, much of it remains there for many hundreds of years. Now, with a number of my social science colleagues, I first started studying what people know about climate and climate change about 30 years ago. And it turns out that now most Americans know those two first facts that I listed. But it also turns out that most Americans do not know this third fact, namely that once the carbon dioxide gets into the atmosphere, much of it stays there for many years. So when we add carbon dioxide to the atmosphere, some of it gets absorbed in the ocean or is taken out by plants. But as I said, most of the balance stays in the atmosphere for hundreds of years, which means that some of the CO2 you are breathing, as you listen to me, was emitted in Britain several hundred years ago during the Industrial Revolution. So there's no single resonance time for carbon dioxide. Here's a plot of how a pulse of CO2 added today decays over time. And you can see that after 100 years, it's down to maybe about 40%, but it's still, a lot of it is still around. Most people think that CO2 stays in the atmosphere about as long as conventional air pollution. This is a piece of work that one of my doctoral students and two of my social science colleagues did a few years ago. The top plot shows judgments about how long carbon dioxide stays in the atmosphere made in a study here in Allegheny County. The bottom plot shows the same result for a national sample. This is the difference in people's estimates of how long air pollution and carbon dioxide stays in the atmosphere. And you can see that about 70% of all respondents, back when we did this around 2018, believed that there wasn't any difference. They rather underestimated, or they rather overestimated how long conventional air pollution stays in the atmosphere, and they dramatically underestimated how long carbon dioxide stays there. To help you think about that, a simple bathtub model can help. Consider the figure on the left, which is the case for regular air pollution. I've got this tap, which is air pollution going into the atmosphere. The atmosphere is the bathtub. And in this case, there's a large drain, and it pretty much drains out at the same rate that I'm putting it in. The figure on the right, on the other hand, is the case of carbon dioxide. Still, we're putting a lot into the bathtub, but the drain, that is, the processes that can remove carbon dioxide from the atmosphere, are much slower. And to stop filling the tub, the faucet has to be almost completely turned off. So here's the bottom line on that first part of the talk. We can argue about how fast we should reduce our emissions of carbon dioxide and other greenhouse gases, how best to make the trade-off between incurring inconvenience and cost today versus leaving a habitable world for our children tomorrow, but neither proceeding full steam ahead with business as usual, pretending there's no problem of climate change, which appears to be the new policy of the U.S. government, nor going along with policy because folks figure that in a few years, when things get really bad, we'll just fix the problem. Neither of those is going to work. All right, so let's me move up. Oops, I'm going in the wrong direction. Sorry. So let me now say also a few background things about the electricity system. The traditional structure of the electricity system looks pretty much like this. We had large central plants. We moved power out across the countryside in high voltage transmission lines. We stepped the voltage down and distribute it to things like factories. We step it down further and distribute it to communities, and ultimately we step it down for use in our homes. Three things to note. There are three conductors, that is three wires on these transmission lines, because we use three-phase alternating current. That's much more efficient for long distance transmission and for many heavy loads like big motors. The second thing to note is that we use high voltage for long distance transmission because the amount of power that you move through a power line is roughly the product of the voltage and the current, but the losses go as the square of the current. So you want to move the power with low losses, which means you want to keep the current low, which means you want to keep the voltage high. And then finally, while many large customers take three-phase power at thousands of volts, most of us at our as residential customers take single-phase power, typically at 240 or 120 volts. Now, that simple model has been getting increasingly complicated. This diagram provides some indication of some of those complications. We've got rooftop solar, we've got distributed resources of all sorts, we've got wind interconnections. All sorts of things are complicating that classic model, and we'll talk in a few minutes about a couple of those issues. These two National Academy consensus studies that I chaired provide background on the U.S. electricity system, and they can be downloaded for free from the website of the National Academy Press. And as Zhenhuo said, he's going to post the slides. So if you would like to look at these, you can then just do a web search for the National Academy Press and download both. So let's move on to why electric power is critical to climate change, starting with the fact that up until now, electricity production has been a leading source of carbon dioxide and other greenhouse gas emissions. So where does CO2 come from in the US and globally? Well, the pie chart shows where it comes from in the US, and the numbers around the outside show the global numbers. And you can see about a quarter of all carbon dioxide comes from electricity generation, both in the US and internationally. This is a model of the US energy system. Along the left-hand side are all the various sources of power: solar, nuclear, natural gas, and so on. And then on the right-hand side, these pink diagrams show the end uses: residential, commercial, industrial, and transport. So look at the bottom, for example, that dark green. Most of our transport is run by petroleum. And on the other hand, notice the gray bar that comes out of the right-hand side of transport. That's rejected energy. Most our internal combustion engines are just not very energy efficient. Engineers make them as efficient as they can, but nevertheless, a significant fraction of the energy we put in as gasoline or as diesel fuel ends up getting emitted as waste heat. The same is true for the electricity system, the orange box at the top. So of the energy that goes in there, the orange bar that comes out of the right, you can see we feed it to residential, commercial, and industrial sectors. That big gray bar, however, is waste heat. And when you drive around the countryside and you see these big cooling towers with evaporative water coming out of the top, that's a strategy for getting rid of that waste heat. Now, again, it's not that engineers are not being really careful to use as much of the energy as they possibly can, but basic thermodynamics essentially means that you can't get more of the energy converted to electricity than is well, we're running at the sort of at the maximum of the current designs. Now, suppose I want to limit carbon dioxide emissions. Incidentally, these are all in quads, which are a funny unit, but basically there are three strategies. We can use more generation that doesn't produce CO2, things like wind and nuclear and solar. We can be careful to not let the CO2 get into the atmosphere when we burn fossil fuels. And we can use electricity that we generate more efficiently so we don't need as much of it. I'll talk first about that last one and then the others. Here, I'm going to show you 4 examples of using electricity more efficiently, and I'm going to spend the bulk of the time on this first plot. This is a plot for refrigerators. The top dark curve is the size of refrigerators. So you can see refrigerators today are bigger than they ever were. The middle blue curve that goes up and then comes down is the amount of energy, the amount of electricity that refrigerators use. And you can see that beginning in the 70s, first because of standards implemented in California, and then because of national standards, the energy used to run a refrigerator has continued to drop. And furthermore, the bottom lighter curve is the price of a refrigerator. And so you can see that today, or at least when this curve was done, but the situation continues to today, as a result of regulation that says you can't market an energy inefficient refrigerator. Today, refrigerators are larger, cost less, and use less energy than ever before. There are other things that we can do as well to use electricity more efficiently. We can use heat pumps. We can convert to solid state lighting. Most of the country has now. And then there are strategies as the system efficiency Vermont has implemented. Vermont, this is the kilowatt hours per customer year in Vermont. And for the US, it in recent years has been growing at sort of a linear rate. It's beginning to pick up a bit more now. The green curve, though, you can see for Vermont is because Vermont takes a few mils of power or of price off each kilowatt hour sold and asks, how could we use this money to better improve the efficiency with which we use electricity in Vermont? So here's how the U.S. generates its electricity today. You can see that up until the late 2000s, coal was the dominant source. But coal has been dropping off and natural gas has been picking up. That's largely driven by economics. Gas has really gotten quite cheap, as I'll say on the next slide. Nuclear has been running about 20%. It's actually dropping a little bit because our nuclear plants are getting old. And here's renewables. Wind is about 10% of total generation. Hydro is of the order of 6%. Solar has been growing, but it's still only about 4%. And so the switch to natural gas that I mentioned in the early 2000s occurred because of the so-called shale gas revolution. Gas prices fell dramatically because reducing electricity, on the other hand, producing electricity with gas produces only about half as much CO2 as using coal. And so some have described that switch as to gas as the bridge to a decarbonized electricity system, which is great. I mean, the fact that we've dropped the carbon intensity of electricity generation by roughly half is a wonderful development. But a bridge needs an abutment at the far end, and so far not much has been done to build that. We've got lots of coal and gas, and while wind and solar should play a much bigger role, we're not likely to be able to completely decarbonize the energy or the electricity system by just using renewables. And that means we need to find ways to use gas and perhaps a bit of coal while not releasing carbon dioxide to the atmosphere. And there are basically three ways to do this. When you download these slides, you can look at them in greater detail. The top way basically says use the fuel in a power plant and then scrub the CO2 out of the exhaust stream of the plant. Now, that's very energy inefficient because most of the exhaust that comes out of a power plant is nitrogen because the atmosphere is mainly nitrogen. And so the carbon dioxide in that exhaust stream is quite there's not a whole lot. The concentration is low. So you really have to work hard to scrub the CO2 out of the exhaust stream. But we're doing it. It's in some plants, and I'll explain that in a moment. The second thing you could do is you could simply break up the atmosphere composition and get pure oxygen. You do the separation before rather than after, and then burn the fossil fuel in pure oxygen. That means you get a much more concentrated stream of CO2 out the back end. And the third strategy, you gasify the fossil fuel, you make hydrogen, which of course, when you combust it with air, with oxygen, makes just water. You do have problems. You have to worry a bit about nitrogen pollutants. So these ideas are not just pie in the sky. Here's a power plant in Texas that's actually doing this. Once you've separated the carbon dioxide, of course, then you have to get rid of it. And basically, the strategy is to inject it into appropriate geologic formations where it will be permanently sequestered at depths of 1 kilometer or so. It rather quickly becomes trapped in the pores, so the risks of any escaping are really, if they're done properly, are really quite modest. And you can see that North America is very fortunate. Both we and the Canadians have quite a lot of appropriate geologic formations. Now, for a long time now, since 1996, in Norway, we've been doing this. The Norwegians passed a rule years ago that said, in your offshore operations that produce natural gas, you can't emit carbon dioxide. And so natural gas in the fields that the Norwegians extract from often is intermixed with carbon dioxide. And so in the Sleipner field off the middle coast of Norway, for years now, we've been separating, or they've been separating the carbon dioxide out of the natural gas and sequestering it by injecting it into a different appropriate formation. Here's another Norwegian plant. This one works a little differently. This is further north. They bring the gas into shore, do the separation on shore, and then ship the gas back, the carbon dioxide back out to inject deep underwater into appropriate geologic formations. We ran a big project on carbon capture and sequestration and published this book some years ago. I want to just draw your attention to one insight from this, that learning takes time. The upper plot shows the capital cost of sulfur dioxide scrubbing technologies for power plants. The lower plot shows the similar curve for NOx, for nitrous oxide emissions. And what you will notice is that though we think about learning curves as starting high and going down, that is, as you build more plants, you get more efficient. In both of these cases, what first happened was the first few plants you built didn't work very well. And so you had to keep redesigning. And then finally you got to a design that worked. And then the efficiency began to kick in as you build more and more. The same will be true for carbon capture and sequestration. And so basically, we need to get started much more quickly. Now, the U.S. and the world has been moving way too slowly on this. There are a few plants around. Many of them are pilots. But nevertheless, if we're going to use this technology, we really need to build more plants at commercial scale. Now, today, most of about 40% of the U.S. electricity is generated carbon-free. And as I said before, about 20%, actually it's been shrinking a little bit, comes from nuclear. I'll mention that in a moment. About 10% from wind and about 3% or 4% from solar. To fully decarbonize by 2035, we'll need to build about 55 gigawatts of new carbon-free electricity every year. And although the U.S. built 60 gigawatts of natural gas generation per year in 1999 and 2000, it has not built more than 15 gigawatts of renewables in any single year. We could do it, but it's going to take a big push. So let me have one slide now on wind, one on solar, and one on nuclear. Wind can play a much bigger role, but this plot shows you the output of an entire wind farm over the course of a full year. And you can see that if you're trying to run a power system where you got to be able to supply power, 24 hours a day, 365 days a year, that there's a problem. You somehow got to deal with all that intermittency. If you happen to be in a place where you got a lot of hydropower, hydroelectric dams, like the Pacific Northwest or Scandinavia, this can be handled. But elsewhere, it becomes a serious problem. And that's one reason that these days there's a lot of attention being paid to storage. The same is true for solar. Here's the output of a single solar rooftop. Well, actually, no, this is a solar farm over the course of a day. And every time a cloud comes by, you can see the output drops again. The map shows where the largest capacity for solar is. The DOE has been working hard to get the cost of solar down, but building the solar farm is only part of the problem. You then got to have storage. You got to deal with the intermittency. One more slide just on nuclear. As the French have clearly shown, despite its various issues, nuclear power is capable of serving a nation's electricity needs without CO2 emission. And in the years past, about 88% of the electricity in France, EDF is Électricité de France, has been generated by nuclear plants. In the U.S., as I've said several times, about 20% of our electricity has been coming from nuclear, and that's great, but these plants are getting old. And we are engaging in life extension, but there is a serious problem of cost control. So the blue bars sticking down are plants we've been shutting down because they've just been getting too old. The two green bars pointing up are the Vogtle plants. They were 7 years late and $17 billion over budget. And so the basic problem that nuclear has is that we have not figured out how to get. There's lots of enthusiasm these days about nuclear power, but until we can get cost control, I don't anticipate a lot of nuclear. Now, there are also the possibilities of small modular reactors and micro reactors. We've done quite a bit of work on these, and the same problem exists in this case. Here's a couple of papers you could look up if you download this slide. This one on the left basically says, we really wish nuclear power could play a significant, make a significant contribution to decarbonizing the energy system, but until costs can be brought under control, we just don't see that happening. So let's move on to the second half of the discussion of electric power. why electricity is the most viable option to replace fossil fuels. So this is the plot that I showed you earlier. And for transportation, of course, we all know about electric vehicles. We can also electrify rail. And in all of these cases, you'll also notice that it says electrofuels. That's using electricity basically to break up water to make hydrogen or some derivative fuel um, to use for combustion. Uh, and I'll let you just quickly look at these others. The electricity sector, it says DAC, that stands for direct air capture. And we talked about that a moment ago for capturing the output from power plants, but I could also capture the CO2 from the atmosphere. That's even less energy efficient than capturing it from the power plant. I'm not going to take time to walk you through all these gory details, but basically the idea is if I have carbon-free electricity from wind or nuclear or something, and I use and I split water, which is H2O, I can get hydrogen, and then I can use that in a variety of different ways in fuel cells, in combustion, and other things to make and I can also, of course, then combine it with carbon dioxide that I take out of the air or out of the seawater and make a hydrocarbon fuel. That doesn't actually remove carbon dioxide from the atmosphere, but it is net zero in the sense that I'm taking CO2 out of the atmosphere, I'm combining it with hydrogen, I'm making a hydrocarbon fuel, burning it in a car or something like that, and the amount of CO2 that in the atmosphere then doesn't go up, it stays unchanged. So we all know about electric vehicles. The advantage of hybrids, especially once you get carbon-free fuels, is that you're not as vulnerable to large-scale power outages. I mean, if you're trying to evacuate the Carolina coast when a hurricane is coming and you got a whole bunch of stranded electric vehicles because they've run out of battery storage, that it's much easier to dump a bit of fuel into a hybrid car than it is to recharge the battery in an electric car. Progress has been slower for heavy freight, but there are prototype systems for heavy trucks that use electricity. And for ocean shipping, which we'll talk a bit more about in a minute, I have two examples. The one on the left, these are both ships run by the Norwegian line Hurtigruten. The one on the left is a diesel-powered vehicle or vessel, but it has a large set of storage batteries, so the diesels can run at a steady speed and be much more efficient. And when you need surge, you take the energy out of the batteries rather than throttling up the diesels. The ship on the right, which is those are solar sails up on the top, that Hurtigruten is working on developing, would actually be completely CO2 neutral, non-emitting. Electrifying rail, as I'll show you in a few minutes, is a whole lot less emitting if the electricity comes from some source that isn't producing carbon dioxide to the atmosphere. We did a study a few years ago on decarbonizing heavy freight. This is a study, again, that you can find if you download the slides, in which we looked at all of the various strategies and look at these X's, these dark X's. Those are rail. All these other things are and ships are actually pretty good too, but all the other stuff off to the right is heavy road freight and medium road freight. Rail is vastly more energy efficient than trucks, and so to the extent that you can move heavy freight off of trucks and onto rail, so-called intermodal, that makes an enormous difference. Let me say one slide on heating and cooling, and then move on to industry, and then finally wrap up. You all know about air source heat pumps, but ground source heat pumps are getting much, much better, and deep ground source heat pumps are even more promising. Not too much of this going on here, but in Europe there is already quite a bit. And then, of course, we already mentioned solid state lighting. Solid state lighting has now made a big impact in terms of reducing or the waste energy from illumination. I have just one slide on heavy industry. First, on making iron and coal. We generate a lot of CO2 from several sources, from making coke, from blast furnaces and similar activities. But rather than using coke, we can do direct reduction with hydrogen that is made with carbon-free electricity. There are a number of pilot plants of this sort being built. Again, the Europeans are taking the lead, but U.S. Steel has been working with one of my colleagues, or some of my colleagues here at Carnegie Mellon, on also exploring these technologies. So there are strategies that clean electricity can be used to decarbonize heavy industry. I'll speak about just one other heavy industry, which is making cement. CO2 is generated from three different sources. This is a cement kiln. You have to decarbonize the decarbonization of limestone. You have to heat the kiln, and you have to then convert that into cement. All of these things take energy. At the moment, we're using natural gas or other fossil fuels. You could decarbonize the production of cement with different feedstocks and electrofuels, and with electricity that's made without emitting carbon dioxide to the atmosphere. Why did I choose just these two examples of heavy industry? Because they, together with petrochemicals and some plastics, are the biggest heavy industry emitters of carbon dioxide. All right, that brings us to the final chunk of this talk. The need to expand electric power transmission capacity, and finally, a few efforts that we're undertaking to address that problem. You might first ask yourself, do we really need more transmission? I mean, you said earlier, we got all these rooftop solar and other things. Can't we just do away with transmission? And the answer is, unfortunately, no. Rooftop solar and distributed resources will help, but we still need to move power to where the loads are, from things like wind farms in the Midwest or offshore wind platforms, from solar in the Southwest, from hydroelectric dams in Canada and in other remote locations. And we also need to assure the continued system resilience. That is, when we have a hurricane or something, we need enough capacity to make sure we can move power from places where we've got it to places where we need it to keep the power system operating. But we face a logjam. It arises from public opposition and legal, regulatory, and other constraints, including the incentives faced by utilities, that makes it difficult, often even impossible, to move clean power from locations where it's produced to the locations where it's needed, while assuring that the power system remains resilient. I'm going to show you two plots. This is the number of miles of higher voltage transmission lines that have been built in recent years, and you can see the numbers have been shrinking. We've hardly been building any, and this is because incentive systems facing utilities, largely implemented by state public utility commissions, have incentivized utilities to make their investments in local upgrades rather than in long distance transmission. We also have a problem that we have so-called interconnection queues that have grown to enormous lengths. If I build a wind farm somewhere or a solar farm, I then have to say, okay, power company, I want to interconnect and ship my power off. And what you can see in this plot is that the number of people who are sitting around waiting for approval to get interconnected has just grown out of sight. And so we got two serious problems here. The Federal Energy Regulatory Commission and a number of Department of Energy national labs and others are working on this issue, but most of what they're doing is pretty incremental, and typically it doesn't contemplate fundamental institutional, legal, or regulatory changes, nor does it address the issue of public understanding and resistance. It therefore fails to address and develop solutions for a number of key issues. Now, in two recent studies, the U.S. Department of Energy has argued that if the economy is going to stay strong and the nation's going to make good progress in reducing its emissions of carbon dioxide, by 2050, the U.S. is going to need to more than double the capacity of our high voltage transmission system. And DOE has laid out a set of optimal ways in which to do this. That's the second report here. You can download both of these reports on the web if you get my slides. However, what neither of these DOE studies does is address the issue of how to actually get these new transmission systems built. And that's what a team we've been assembling proposes to do. With several colleagues, we're working to create a multidisciplinary, multi-institutional consortium that will identify and facilitate solutions to the problem of expanding U.S. transmission capacity. While a solid technical and economic underpinning will be essential, we see the challenge as studying public perceptions and improving public understanding of the need for expanded transmission, assessing legal, regulatory, institutional, and political obstacles and those arising from interest groups, and then proposing and actively promoting needed fundamental structural, legal, regulatory, public communication, and policy changes. Public perception and improving public understanding is particularly important. There haven't been a lot of studies in the U.S. recently in this area. There have been some in Europe, but the situation in Europe is quite different. So with a colleague who is a behavioral social scientist at the University of Southern California, we're now designing such studies. While it's important to continue to work on facilitating the construction of new conventional overhead high voltage AC transmission lines, we think it's also important to complement that work by doing two things: developing ways to expand the amount of power that can be moved through existing transmission corridors, and using high voltage DC cables embedded in both traditional and non-traditional rights of way. I've got a slide on each of these, and then we're going to wrap up. More power through existing rights of way. Well, we gather a whole lot of data these days from power lines. We're maybe not using it, shouldn't say maybe. We're not using it as effectively as we can. Using it with making greater use of it, we can up the capacity. We can upgrade the capacity of existing high voltage AC lines by, for example, converting the conductors to things that don't sag when they get heated up, so you can run more current through them. Or we can convert high voltage AC lines to high voltage DC lines. We're not doing that in this country, but there are a couple of examples around the world where that is happening. Here are 3 papers you can download to take a look at that discuss those issues. The second strategy I mentioned is moving more power via high voltage DC cables in traditional and non-traditional rights of way. Things like burying these along lower voltage transmission corridors, along highways, in waterways, and so on. Here's a system that's being constructed right now to bring hydropower down from Quebec to New York City by burying cables under Lake Champlain and then burying cables under the Hudson River. Here's another system that's been proposed to move power from wind in the Midwest to load centers further east. And so the work we're planning will address 4 different things: improve public understanding, and then analysis of expanding in traditional rights of way and then in non-traditional rights of way. And by the end of this project, we plan to have created material to improve public understanding of the need for expanded transmission capacity and together with the pros and cons that also offer discussions of the pros and cons of different ways of doing that, and having systematically identified legal, regulatory, and other barriers to expanding transmission, we will then work on developing recommendations for how that might best be done. And that concludes my talk. There are two final slides which I'm not going to talk about, which are a PS on the some of the other work we've done. But at this point, I'm going to take my slides down and let you folks ask questions.
Yeah, thank you so very much for your fantastic talk, and really appreciate, and it's very informative, very inspiring and insightful. Now it's time for questions. Again, the audience is welcome to post questions in the Q&A box. And there are already questions in the Q&A box. And let's see. The first couple questions from Tom Dees. He said, wonderful talk. As usual, learned a lot from you. Two questions. First, a few years ago, we estimated that just getting U.S. housing up to on the shelf tech would reduce U.S. emissions by about 7%. The Vermont program you noted is nice but modest, and it seems the public acceptance is high. The question is, should we do more research and promotion on emission? How far could we get with strong research and the implementation on efficiency?
Well, I missed the very beginning of that question. It's a question about improved efficiency.
Yeah. So how should we do more research and promotion on
Yeah. Well,
emission?
and the answer is an obvious yes. I mean, there are limits. You do need energy to do stuff, but as you saw in that diagram, the sort of spaghetti diagram of the U.S. energy system, there are a variety of things we can do. We've already, I mean, the refrigerator example that I cited is a good one, but we could do the same thing, and we are to some degree doing the same thing for lots of other things. And the DOE, the Department of Energy National Labs, for example, have big programs trying to figure out how to make homes more efficient. I mean, the simple answer is yes. We definitely need more research on this, but we also need activities that promote its adoption and use. I mean, if I call up my local home heating company and ask them to replace my furnace, they're not initially going to say, why don't you put in a ground source heat pump? They're going to say, why don't you put in a reasonably efficient gas furnace? And the number of contractors who are actually capable of putting in these things, let alone, for example, DC distribution circuits in buildings, is very small. And so there are big obstacles to implementing the stuff we've already got. Next question.
Yeah, the next one is, he said, what do we know about the sources of public resistance and what we can do to resolve the objections?
If by public resistance you mean to constructing transmission, the situation is that there have been half a dozen studies in recent years in Germany and Switzerland, but virtually none here in North America. And we have been trying to get resources. We think we are about to get some resources from the Alfred P. Sloan Foundation to design studies. We're still looking for resources to actually conduct the studies of public understanding. Our suspicion going in is that though they'll be more expensive, buried cables will be much more acceptable to most people than overhead transmission lines. And so if you can't build the new overhead line, it may be worth spending more to put in a buried cable system. But at the moment, the incentive structures aren't set up to really easily make that possible. On the broader issues of public acceptance, that is the decarbonization of the broader energy system, that's a very large topic, and there's been lots of studies of this. people do now, for the most part, as I said in my early slides, understand that there is a serious climate problem and that we got to get going on it. But of course, it's a trade-off between things in the short term and handing a livable planet to our grandchildren in the long term.
Yeah, wonderful. Thank you. The next question is from Doug Bissett. Thanks so much for your talk. How optimistic are you that the carbon capture and storage, which no matter how efficient, will always increase the cost of electricity and produce a valueless product unless it's used in enhanced oil recovery? Will ever be meaningfully prioritized by either political party in the US? And what about both the technical and perceived risk that accompany CO2 storage?
As long as it's free to emit carbon dioxide into the atmosphere, carbon capture and deep geologic sequestration is simply not going to happen. I mean, it's happening at pilot scales. We're running small demonstrations, and direct air capture from the atmosphere is also happening. I mean, there's a European company that has installed one modest pilot plant in Iceland and is building a much larger one. But the basic situation is that as long as I can emit carbon dioxide to the atmosphere without any cost, I'm not going to invest a lot of money in that. Now, posit for a moment that either it becomes illegal or there's a high cost to emitting carbon dioxide to the atmosphere, then people could begin to get serious. As the questioner suggests, there are all sorts. Well, let me actually also say a comment about using captured CO2 for enhanced oil recovery. That, of course, is net carbon dioxide positive. For those who don't know about this, if I pump CO2 into oil fields under high pressure, I can extract more oil. So I've put the CO2 in the ground, but I've also produced a whole lot more oil, which I'm now going to burn. And so on net, that process results in increasing the amount of CO2 in the atmosphere. There are lots of difficulties with implementing carbon capture and sequestration. Even if we had laws or carbon taxes or something else that said I can't emit CO2 to the atmosphere for free, there are enormous obstacles that need to be overcome. And that's why I stressed the importance of getting started early. Now, Ahmed Abdullah, who is on the faculty at Carleton University in Canada, gave a wonderful talk in our department just yesterday with one of his colleagues on all of the issues associated with adopting CCS in Canada. And there are many issues. And so the notion that you could simply turn this on is obviously wrong. But if we don't get started, we will simply not know how much we can implement to reduce CO2 emissions in this way. Shingo, go ahead.
Thank you so much. Yeah, the next question is from anonymous attendees. You mentioned that many people are switching to heat pumps in their homes. Do you think that this is a cost-effective switch for people in colder places, like in Alaska, for example, that may also need to rely on natural gas to heat their homes?
Well, heat pumps are getting much better over time. If you want to find somebody who knows a whole lot about this at your companion institution, the University of Michigan, Parth Vyazhnev has been doing lots of interesting work on the current and evolving state of heat pumps. Heat pumps are getting better in terms of dealing with colder weather. My son, for example, has a ground source heat pump that can do reasonably well in New Hampshire, but they do have to use natural gas. Uh, the key point is that one needs to continue to push the technology forward. And in much of the U.S. today, heat pumps are probably an adequate solution. In places like Minnesota or northern New Hampshire, the technology isn't there yet, but the Department of Energy has had a major program to try to push the efficiency up. Whether that program or what the future of that program will look like in the coming few years is less clear, given the enormous changes afoot in the federal government.
Yeah, great. Thank you. The next question also from anonymous attendees. He said, or she said, great talk. It seems that your three strategies were missing one other solution. Use less electricity. It is necessary to go carbon-free, but I fear swapping everything with a renewable will push the problem further down the chain. Do you think there are ways to simply reduce global electricity and power? Perhaps policy to limit power consumption of data centers and incentivize public transportation could be stopped. This is a tough issue with economic competitiveness, and I imagine this is where the log jams you mentioned in your talk.
Yes, I agree that using less electricity, which is why I talked at the very beginning of the section on electricity of things like refrigerators, that is the notion of improvements in energy efficiency um, uh, are so very important as part of the mix. I mean, for years we've understood that public transport is much more energy efficient than individual cars, especially individual gasoline or diesel cars. It's been really hard to move people into public transport. But the simple answer to your question is yes, we can certainly pursue a variety of strategies to use less electricity. But for things like heavy industry, it's not clear how you substitute for fossil fuels other than with ultimately carbon-free electricity. But to the extent that you and others can figure out how to promote a lifestyle that uses less electricity, that's great.
Yeah, thank you so much. Actually, the next question is related to this question. This question said, I often say conservation is potentially the largest source of carbon-free energy, but you did not address that. What about changing the habit of use energy? Our use models are always built on pro-growth habits. We are a pretty wasteful society, and that applies to energy use too. All solutions are not technological. Why not address that?
Yeah, well, good luck. We've had a variety of doctoral students in my department. I'm in a department here called Engineering and Public Policy that works on a lot of these issues. And we've had quite a few doctoral students who wanted to work on changing people's preferences and habits. It's hard going. And so while you can do some of that, it's also the case that, and by changing the broader incentive structures, you can also modify things. I mean, the previous question about public transport, yes, that's an enormous improvement in efficiency in energy use or reduction in energy use if you can get everybody to use the bus. When I go downtown from Carnegie Mellon, I go down on the bus because I don't want to drive down, and it's more energy efficient. But getting people to change their habits is really tough. So you should continue. Don't abandon that. Figure out how to make incentive structures to encourage more energy efficient activities, but at the same time, figure out also how to make the the system also use the energy that we do need more efficiently. We got a time for one or two more?
Yeah, okay. The next question is from Sharath from India. The question is, how do you suggest a countries like India, which has a huge demand for electricity in terms of population and industry, to reduce CO2 emission?
So look into an outfit in Bangalore called CSTEP, Center for Science Technology Policy, which is staffed by a bunch of the doctoral students who've come out of our department and who have done extensive work on issues. But India, of course, is heavily coal dependent. Uh, One of the strategies for reducing local emissions is when a ship comes to shore. For example, when a ship comes into Long Beach, California, it's required to turn its diesels off and get its electricity from the shore. So we had a doctoral student a few years ago who looked into whether doing that in India might make sense. And it turns out the answer is no, because Indian electric power generated by coal-fired power plants is so much dirtier than the diesels in the port that it really doesn't make much sense. But India is working hard on renewables. And as I said, sorry to sort of duck, but contact the folks at CSTEP, Center for Science Technology Policy in Bangalore. They really are on top of a lot of this work, and they've published many very interesting and useful reports on problems related to decarbonizing India.
Great, thank you so much. The next question is from anonymous attendees. Is there a risk of the United States falling behind in small modular reactors technology? With the abundance of cheap natural gas, our reliance on them stagnate our energy sectors?
I mean, the answer is yes. Um, there's a risk of the U.S. falling behind more broadly in nuclear technology. We did a piece of work. If you send me I'm on the web, so you can find me. If you send me an email, I can point you to a piece we did more generally about. I mean, the U.S., for example, in the nuclear space, has long led the world in terms of concerns about the diversion of nuclear materials. But we're not building nuclear plants. We are in early development stages of a lot of small modular reactors, although the only reactor NuScale that is approved by the Nuclear Regulatory Commission has been, I mean, its most recent larger project got canceled because cost control became a serious problem. But the simple answer is yes. There is some significant risk that the U.S. will lose its lead, but it has lost its lead in the nuclear space. And I'd be happy to point you to a couple of papers that talk about those risks. But the key focus, I mean, if you listen to the Department of Energy over the past few years, the nuclear programs there, they're all full of high-tech, wonderful stuff, but almost no attention to how do I build a plant and keep the costs under control. And until we can do that, I mean, I would love to see the U.S. increase the share of carbon-free nuclear. But until we can figure out how to get costs controlled, I just don't see it happening.
Thank you. We are a few minutes over, but could you take another question?
Yeah, I can take a couple more.
Okay.
Still got an audience.
Yeah. So from anonymous attendees, great presentation. Thank you for blending the political hurdles with the technology opportunities. Any thoughts on how to depoliticize the narrative on different energy generation options, especially in the current environment of the federal government pulling back on the Infrastructure Investment and Jobs Act investment in solar energy and wind energy?
Not yet, really. I mean, we're only a few months into this new administration. My guess is that that many folks around the country, Republicans as well as Democrats, are going to come to understand that uh, some of new, more uh, the new cleaner, more efficient energy technologies are things it's worth pursuing for the country, and that there may well be also outside of the U.S. export markets for these technologies. But at this stage, uh, I think we just have to let things equilibrate for a bit in Washington. I don't even know. I mean, you know, on a daily basis, we're hearing all sorts of new things, and until it settles down a little bit in the policy space, it's not clear to me what the best options are. But my suspicion is that there will be a lot of action at the state level, and that increasingly uh, people, once they sort of get back past their ideological hangups, will begin to figure out we got to have cheap, clean energy, and we'll begin to pull together to try to make that happen. Sorry that I can't offer you a more specific or optimistic argument, but I think, like most of the rest of us, we just don't know yet.
The next question you will know a lot. Your Center for Climate and Energy Decision Making has been in operation since 2015. And how have you been able to run your center so successfully and for so long?
Well, there were three centers, and they were NSF supported. In about a year and a half or 2 years ago, the NSF decided they weren't going to continue to support centers like this. And so that particular center with NSF support no longer exists. If you, on the other hand, take a look at the book, there's literally many hundreds of refereed publications in the back that sort of lay the foundation for a lot of work. We are going forward to work on this problem of transmission capacity. I've pretty much concluded that we're going to need private foundation support because, I mean, we've tried several iterations with National Science Foundation, and the reactions are, what's the theory you're advancing? Or this is too applied. So we're trying one more right now, but I expect to be declined again. It's the Alfred P. Sloan Foundation, as I indicated, has provided us with a seed grant to get started. And my guess is that for this transmission capacity expansion work, we're largely going to have to depend for at least the next few years on foundation and other private funds rather than on federal monies, particularly given what's happening to the budgets at places like NSF and the Department of Energy. The Department of Energy will obviously perhaps appropriately first try to make sure that the work of the national labs doesn't get too badly disrupted. But we're in for a period of rather deep uncertainty, I think.
Thank you. Back to the last question. Okay. Back to the title of your talk. You say the electricity without the greenhouse gas is a great idea. However, electricity without the greenhouse gases for one country may generate more greenhouse gases in other countries. For example, one country may import product manufactured in other countries which may use fossil fuel and generate more greenhouse gases like CO2. So the global energy transition to electricity without the greenhouse gases may be compromised. How to avoid this kind of spillover effect and how to achieve global energy transition to electricity without greenhouse gases?
Years and years ago, I published an opinion piece in the journal Science titled Managing Carbon from the Bottom Up, which argued that if you look at where the carbon dioxide emissions around the world come from, they really only the bulk of them come from only a handful of countries. So the first observation is, yes, we ought to continue with the the cops and all of these, hundreds of people in a room trying to negotiate arrangements. But if we really want to solve the climate problem, what we need to do is get CO2 emissions under control in half a dozen major emitting countries. China, for example, despite all of the tensions between the West and China, has actually made a lot of progress in terms of lowering the carbon intensity of the Chinese economy, and I suspect will increasingly over the coming decades actually manage to get emissions reduced. But to go back to the thrust of the question, the other issue is, continue to put effort into the COPs and the international negotiations, but focus on trying to build coalitions, maybe even just between a few regions that focus on this, and then also develop technology. So, to go back to the question about India, one of the reasons that it's expensive for India to decarbonize is that a lot of these technologies really cost a lot. And so to the extent that we can develop and demonstrate lower cost ways to achieve these things, then the rest of the world can presumably follow. The basic difficulty, though, that I mentioned at the very beginning of my talk is that once you put the CO2 in the atmosphere, a lot of it is there for a long, long time. And so the longer we stall off, the harder it's going to be to address this issue. And the notion that we can, in the US, for example, proceed for the next 4 years or so, ignoring the climate problem and just continuing to do fossil fuel business as usual, is just going to make life so much harder for our grandchildren.
Yeah, thank you so very much again, Professor Morgan, for your wonderful talk and Q&A questions. So interesting. We have to stop here now because we will run out the time. We're 11 minutes over. So also I want to thank the audience for the active participation. And so we have to say goodbye now. And so everybody, and enjoy the wonderful day and or evening, depending where you are. So thank you so much. Bye-bye.
Bye-bye.